Okay, so this is going to be section 10.4. We're now going to be talking about the areas and lengths in polar coordinates. In order to do that, we need to start talking about the calculus that's going to be used. This section is pretty involved. Definitely involves a lot of trig because we're talking about polar. It's also going to involve a lot of trig identities, which may be something that you're not quite as comfortable with at this point, or you just didn't cover as much or whatever. But we're going to go back through those, and you will have to be able to use some of those things to be able to do this, as well as all of your other antiderivative techniques that we've talked about to this point. So again, it is pretty involved because it involves a lot of different things. It starts kind of wrapping a whole bunch of stuff into one section here. This will be definitely day one will be multiple videos, two, maybe three, hopefully not more than that. Um, we'll see how it goes because some of the examples can take a long time to get through. They are relatively algebra and trig intensive. All right, so let's start off by talking about the derivatives in polar coordinates. So just like anything else, even with a polar equation, you can find the slope at any given point on a polar curve, which really should make sense. Again, it's going to have a slope someplace. Um, so to find dy over dx, it's basically just like it was in parametrics, where it's going to be the derivative of y and the derivative of x, each with respect to theta now because it's in polar coordinates. So it'll be the change of y with respect to theta over the change of x with respect to theta, or dy over d theta over dx over d theta. Again, very similar to what it was in parametrics. Again, this is just kind of an extension of that. Parametrics, it was dy over dt over dx over dt, same concept. The biggest thing is that is technically the slope, but it's not very usable. Okay, we have to be able to figure out what dy over d theta and dx over d theta are in better terms in order to do this. The formula itself looks really long and cumbersome, but if you understand the basic concept of the product rule, and we all should at this point, that's how this whole thing is derived. So let's go ahead and take a look at that real quick. Y, we know to be r sine of theta, okay? But r is another way of saying f of theta, very much just like if you said y equals some function of x, y and f of x are usually kind of synonymous. Well, in this case, we're going to say y equals r theta, but we're going to say r as f of theta. I'm sorry, not y equals r theta, y equals r sine theta. But instead of saying r, we're going to say f of theta, and then it's sine theta. Similarly with x, x is going to be r cosine theta, but again, r we're going to replace with f of theta cosine theta. Okay, none of that should really be all that difficult. Now let's look at how we actually find this. So we want to take dy over d theta. We want to take the derivative of this thing right here with respect to theta. What you should notice is I have f of theta times sine of theta. That's a product rule. So we have to incorporate the product rule when we do this. So we will do the derivative of the first function, f of theta. Well, that's just f prime of theta times the second function, sine of theta, plus the derivative of the second function, sine of theta, is cosine of theta, times the first function, f of theta. Okay, that's the numerator. That's your dy over d theta. Now we have to do dx over d theta, which is going to be the same exact concept. We're just going to deal with the x function. Again, it is a product rule. So the denominator is the derivative of the first function is f prime of theta times times the second function, cosine of theta, plus the derivative of cosine, which is negative sine. So I'm going to write the negative here. Write that a little bit better. Sine of theta times the first function, which is f of theta. So that right there is your equation for finding the derivative in polar. dy over dx is the same thing as f prime theta sine of theta plus f of theta cosine of theta all over f prime theta cosine of theta minus f of theta sine theta. Again, looks very cumbersome. It's a big formula, but if you figure out that it's just using the y equals r sine theta, x equals r cosine theta, changing r to f of theta, it's the same thing, and then doing a product rule in the numerator and denominator, that's how you get it. So you don't have to memorize it if you can figure out. However, if you choose to memorize it, by all means, go ahead and do so, because there are patterns to it as well, and you can hopefully see where some of those patterns are. So that pretty much takes care of all of that right there. All right. It says in number 2, basically the same as parametrics. I've kind of already gone over that stuff. You can use the same method as with parametric equations to find vertical and horizontal tangents, meaning if you want something to have a horizontal tangent, that means that the numerator of your derivative needs to be 0 without the denominator being 0. So you would set dy over dt equal to 0. In this case, you would do dy over d theta equals 0. And then for a vertical tangent, dx over d theta would have to be 0, again, as long as the numerator portion is not 0. So they both can't be 0 at the same time. So that's how you would find vertical and horizontal tangents using this derivative. And don't worry, we're going to practice at least one of these here. All right, and the last concept, which we'll talk about here, and we'll actually get into a little bit more in a further example, is finding what's called a tangent at the pole. And a tangent at the pole occurs, and this is supposed to be an alpha, it just doesn't look like it very well. If alpha, which is an angle, is a solution to f of theta equals 0, and f prime of theta does not equal 0, then theta equals alpha is a tangent line at the pole. Again, I'll talk about what that actually means when we get to that example. What does it mean to have a tangent line at the pole? But to figure it out, the original function f of theta needs to equal 0, and f prime of theta cannot equal 0 at those theta values. Those are the two important things. All right, we'll get to that example in a few minutes. Our first example here, number 1, differentiate the polar equation r equals 2 sine theta, or basically we are trying to find dy over dx. All right, so just for this purpose here, we're going to rewrite what we just put on the other side. Dy over dx equals, again, it's dy over d theta over dx over d theta, but on the other page we wrote that as f prime of theta sine of theta plus f of theta cosine of theta, all divided by f prime of theta cosine of theta minus f of theta sine of theta. Okay, so let's see what we've got here. R equals 2 sine of theta. So f prime of theta, remember that f of theta is the same as r, so you could just say f of theta is 2 sine of theta, if that helps. So f prime of theta is going to be 2 cosine of theta. And actually, that's pretty much all we need in this case, because we've got everything else that we need. We have f of theta. We now have f prime of theta. Sine and cosine of theta are just what they say. So let's go ahead and put these things in. So we've got f prime of theta, which is 2 cosine of theta times sine of theta, plus f of theta, which is 2 sine of theta times cosine of theta, all over f prime of theta, which is 2 cosine of theta times another cosine of theta, minus f of theta, which is 2 sine of theta times sine of theta. And that is your derivative. Okay, now that is not simplified, and this is where we're going to start using some of our identities, but that is the derivative. And if you had theta, you can just plug all the theta values in and simplify it from there. You don't have to do any further algebra at this point. But we're going to simplify this thing because we don't have a theta value. So we're just going to figure out what we have here. So on the top, we've got 2 cosine of theta sine of theta plus 2 sine of theta cosine of theta. Well, it's the same thing. So now we're going to have 4 of them. Does not matter which order we write the sine or cosine in. And in the denominator, we've got 2 cosine squared of theta minus 2 sine squared of theta. If that was plus, this would be much nicer, but it isn't. All right, we can still simplify though. So it looks like I can divide a 2 out of every term. So now we're going to get 2 sine of theta cosine of theta on the top. Dividing a 2 out of each of the terms on the bottom, we get cosine squared of theta minus sine squared of theta. All right, so this is where our trig identities are going to come into play. One of the nicer trig identities to be able to use here is that numerator, 2 sine theta cosine theta, I'm going to write these at the top of the page here just so you have this, 2 sine of theta cosine of theta actually simplifies to sine of 2 theta. It's a double angle. And then cosine squared minus sine squared. And yes, it has to be in that order. If it's sine squared minus cosine squared, it's going to be the opposite here. It's going to be negative. But cosine squared minus sine squared happens to be cosine of the double angle. Okay, again, if the sine squared and the cosine squared were flipped and it was sine squared minus cosine squared, that would be the negative cosine of 2 theta. But in this case, it is not. So this simplifies down here. We've got the first one on the top, which is sine of 2 theta. And then the bottom one is cosine of 2 theta. Since the angles are the same, these are the same types of functions, so we can do sine divided by cosine, which in this case is just tangent. And it's tangent of the angle 2 theta. So our derivative, dy over dx, of r equals 2 sine of theta is tangent of 2 theta. So in other words, you could find the slope at any given angle based upon this. All right, one of the nice things about this example, and I really don't know why I haven't taken this example out of there because I don't ever use it, it says find the second derivative of r equals 2 sine of theta. We are actually skipping that. Not that it doesn't have any uses, but I am not going to do anything with it. Second derivatives, just like before, can be done, but I am not going to specifically do anything with the second derivative here. So we are skipping example 2. And we're going to move on to example 3, which says, for the polar curve r equals cosine of 2 theta between 0 and 2 pi, find the equations for all the tangent lines at the pole or at the origin. So now I'm going to try and explain a little bit more about what this means, and then this will probably be the last one for this video. So this is the idea. First of all, if you were to graph this, I am not going to pull up the calculator to do this, but you can plug that into your calculator, r equals cosine of 2 theta. If you remember, it is a double angle in its cosine, so it is going to be symmetric to the x-axis. It's going to have 4 petals because it's an even angle in there, so we're going to double it, and it's actually going to look something like this. It's going to be one of those 4-petaled roses. I'm doing my best to try and get, that's horrible, but it's good enough. So this is what this means. We want to find all of the tangent lines at the pole. The idea is your tangent line is only going to hit your curve at the pole, which means it's only going to intersect your curve at the center. I have tangent lines all over this thing, right? There's a tangent line that goes through here. There's a tangent line which goes through here. There's a tangent line which hits this spot down here. There's all these different tangent lines, which I'm going to erase. that hit the curve, but there's only going to be certain ones, sometimes never, but in this case, only certain ones that actually are going to hit the pole. If you remember, the criteria was whatever f of theta equals 0, so we have to find that first, and then we have to make sure that f prime of theta does not equal 0 at those places. So first, let's find f of theta equals 0. So f of theta equals 0 when cosine of 2 theta is equal to 0. Remember, we only want these values between 0 and 2 pi. That helps because otherwise you could technically have an infinite number. So we're going to set 2 theta, because that's our angle, equal to whatever makes cosine 0. Remember, cosine is 0 at all the odd pi halves. So that's going to be pi halves, 3 pi halves, 5 pi halves, 7 pi halves, and so on. Now, when we simplify this, we want to make sure that our values are only the values in between 0 and 2 pi. Well, we have to divide by 2 to actually find theta. So if we divide everything by 2, we now get pi fourths, 3 pi fourths, 5 pi fourths, and 7 pi fourths. If we had gone any further, we would be outside of our domain. So we can't do that. So this is it. Now what we have to do is we have to check to make sure that none of those make f prime of theta equal to 0. So let's find f prime of theta. F prime of theta, not to be confused with dy over dx. That's the slope at any point. This is just the derivative of our r value with respect to theta only, not the same thing. So f prime of theta is going to be the derivative of r with respect to theta. It's a little bit of a chain rule. It's going to be negative sine of 2 theta times the derivative of 2 theta, which is 2. Now you can either set that equal to 0, find all the values that make that 0, or you can just plug in the values that we have for theta and make sure none of those give us 0. Well, if you plug in pi fourths, 3 pi fourths, 5 pi fourths, 7 pi fourths in for theta, you're basically going to have a 2 introduced on the top, which is going to reduce your denominators all to 2. So you're going to get pi halves, 3 pi halves, 5 pi halves, 7 pi halves. At all the pi halves, sign is either 1 or negative 1. So none of these values that we have found are going to make our derivative equal to 0. So all of these are solutions or tangents at the pole. Visually, what does that mean? Well, if theta equals pi fourths, again, had my drawing been better, this would look better, but if theta equals pi fourths, that is going to start right at the pole, and the angle will go out at a 45-degree angle. Technically, it should really only touch these two curves as they curl in towards the pole at the pole. Mine doesn't do that because I can't draw very well, but that's the general idea. 3 pi fourths, same thing. Only touches at the pole, extends out that way. 5 pi fourths, same thing. 7 pi fourths, same thing. So those are what are considered to be tangents at the pole. All right, that is plenty enough for this video. We'll come back with example 4, and we will start the idea of how to find area.